Hi everyone, I'm Sophia. I'm a junior at Weston High School, and this is Eva.
Hi, I'm Eva. I'm a senior at Weston High School.
And we're here to present our talk as a part of Ageless Science. We are the co-presidents of Ageless Science, which is a nonprofit, and we go to many different retirement homes to lead engaging discussions with different residents. And we're really excited to present our most recent talk on batteries. It's about how batteries are sourced, the sustainability factor behind batteries, and some upcoming technologies that look really promising.
Yeah, and a little bit about us. So like we said, we're both from Weston High School, and we're involved in a lot of STEM stuff in our school. We both love science, technology, engineering, and math. And we're actually both captains on our robotics team in our town. In my free time, I'm the president of the coding club as well. And outside of school, I love doing things like hunting down froyo. We're both big fans of froyo places, so yeah.
Yeah, we're so excited to introduce this talk. Thank you so much for listening.
All right, then, I think we should get started. Today, our talk is about batteries, and this is a topic that we chose because so many people, we all use batteries every day in our lives, and they're everywhere. We don't even think about them. But a lot of us don't know much about batteries, and so we kind of wanted to explore the power behind our everyday lives. So today, we're going to cover four main areas. First, we're going to introduce you all briefly to batteries. Then Sophia is going to talk a little bit about the different types of batteries and some sustainability methods. And then I'll talk about some future technologies. Okay, before we get into it, we kind of have to understand how batteries work at a basic level. So at a high overview, batteries turn chemical potential energy into electrical energy. And to understand how they do this, we have to know a little bit of chemistry. So in chemistry, we understand that everything that we know is made up of atoms, and charged atoms are called ions. And at two ends of a battery, there's chemical potential energy is created by a difference in charge. Because as you guys know, like charges repel, opposite charges attract. So by separating a lot of positive charge and a lot of negative charge, you create that potential energy. And there are three main sections to a battery. What is called the cathode, the anode, and the electrolyte, which is in between the two. So the anode is the negatively charged portion of the battery. The cathode is the positively charged portion of the battery. And the way the battery works is that through a series of chemical reactions, it creates this difference in charge, and then it allows electrons, which are negatively charged subatomic particles, to travel from one end to the other. And as those electrons move, they create what is called electrical current. We use electrical current to do work, right? So say you have the negatively charged anode, which you can see here, and the positively charged cathode, and then we take a material that electrons can move through very easily. That's called a conductor, typically copper, maybe silver in wires. And those electrons move through that wire. And say now that we put something like a light bulb in the way of those electrons. Well, they really want to go to the positive end, the cathode of the battery. And so they're forced to move through that light bulb. And when they do that, they make the light bulb glow for us. So that's kind of the most basic example of how we do work with batteries and what's happening at that chemical level. And the chemical reactions that I was talking about earlier, there are two main types that you need to understand for the use of batteries, and one is called oxidation. That's when you put in some chemicals and you get out some chemicals and a bunch of extra electrons. So oxidation happens in the anode, and when that chemical reaction takes place, a bunch of electrons are produced. That's what makes the anode negatively charged and allows the electrons to flow from the anode to the cathode. Now, in the cathode, reduction takes place. That's the opposite idea. reduction kind of soaks up those electrons. Electrons, along with some chemicals, go into reaction, and they come out, and it's just some chemicals. So those electrons have been absorbed, taken in by the atoms. And there's also two types of batteries, which Sophia will talk about later, but some batteries can be recharged, right? And when batteries are recharged, it is literally this exact process, except in reverse, right? So you can imagine as the battery is used up and more electrons flow to the cathode, you kind of run out of chemicals to do all these reactions with, and that's how batteries get used up. And the rechargeable batteries that we use in our phones, maybe in our smartwatches, and other things like that, are designed so that those reactions can go in reverse. And when you apply electrical current to the system, all those equations kind of go backwards, and it resets the battery. However, one thing to keep in mind is that there is no 100% efficient process, right? So we start with a certain amount of energy, but the more we kind of use up the battery and then recharge it and then use it up and recharge it, we kind of lose a little bit of energy each time, because there's always energy that is lost to resistance, that is lost to heat, and so nothing is ever quite perfect, and that's why our batteries deteriorate a little bit over time. And this is what the inside of a battery really looks like. So the previous slide, which had the cathode, the anode, and the electrolyte, was a bit of a basic overview of a battery, right? Those were really the essentials. And that's not what a battery would look like if you really opened it up. So this is what a battery looks like if you take your typical AA, AAA batteries at home and you cracked them open. Don't do that. This is what is inside. And it still has the basic layout of cathode, anode, and electrolyte. So you can see here that the anode is kind of in the center of this cylinder, and it's made of zinc in this case. And when the oxidation occurs and a bunch of free electrons are kind of generated, they jump onto this brass pin here, and they travel down, and this is the anode at the bottom, and at the top is the cathode. So that's how the cathode is positively charged and the anode is negatively charged. So I just wanted you all to see that. And this is kind of a complex technology, right? You might be looking at this thinking like, whoa, how did we get here, right? How did we discover this? Who put this together? So I want to walk through a bit of a brief history of how we have reached the batteries that we use and know and love today. So one of the earliest discoveries of a battery actually comes in the form of an artifact. This is probably a lot older than any of you would ever imagine a battery would be. It's a little bit over 2,000 years old. It dates back to about 250 BCE. And this artifact is called the Baghdad battery because it was discovered around the Baghdad area. And it's a very, as you can imagine, kind of crude form of a battery. It's like a clay pot. It's got like an iron pin in it, and when you fill it up with vinegar, it produces 1.1 volts. Now, this is pretty interesting because the batteries that we use today, a lot of them typically produce around 1.5 volts. The difference mainly comes in the fact that our batteries today are designed to be much, much more efficient with a lot less resistance, and they're a lot smaller than a big clay pot. One interesting thing about the Baghdad battery is that at this time, there was no real use for batteries, right? As you can imagine, all the way back then, they didn't have phones to charge, they didn't have electronics to run. So one of the things that still mystifies historians about the Baghdad battery is what its real use was. And that remains a bit of a mystery today. In fact, there was one historian who proposed that the Baghdad battery wasn't really a battery and it was just used for storing scrolls, which is quite interesting. But it functions as a battery nonetheless. So a lot later, in 1800, Alessandro Volta, who the unit volt is named after, had the first real discovery of the battery, what we consider the invention, the discovery of the battery. And he kind of discovered that when copper and zinc are placed in an electrolytic solution, that the copper atoms didn't break down, but the zinc atoms broke down and caused a lot of electrons to flow out of them. And that was the basis of the whole anode and the cathode, right? That's how we got that electric potential difference. And this actually forms the basis, this technology, this idea forms the basis of our modern batteries today, the stuff that you guys use, although it's a little bit different. And then a little bit later, there was another notable invention, which is called the Leclanche cell, if I'm pronouncing that right. Hopefully I am. So George Leclanche invented this cell, and it's very similar to the Volta battery. It was based on the Volta battery, but it's a lot more, it was more improved and more accessible for consumer use and wide-scale production and use. And it was kind of the same setup. It was manganese mixed with a little copper on the negative side. Sorry, it was it was zinc on the negative side, and the positive side was manganese mixed with a little copper, mixed with a little carbon rather than copper that you see in the Volta battery, right? And fun fact about these is these were actually used to power like phone calls and cell lines, and one of their biggest downfalls was that they kind of ran out quickly. So when you use a battery for a long time, those chemicals get used up and the voltage starts to drop a bit, and this is what caused the Leclanche cell to not be so good. People couldn't make long phone calls. They had to keep it brief. So yeah.
Cut right off in the middle of the sentence.
Yeah. And I just wanted you to take a look at this Baghdad battery so you have a visual of what is considered the very first battery ever. And I think it's funny that you can see a lot of similarities, if you go back 2 slides really quickly, between this original kind of crude making of a battery and the ones that we use today. You can kind of see a lot of similar structures. So I just wanted you to have that visual. And now I'm going to turn it over to Sophia to talk about...
Like at the bottom of the battery, what was all the mechanism down there?
Yeah, so this is a clay jar. All this gray stuff on the outside is a clay jar. And this stopper here at the top, which holds the metal bar, it's made of asphalt. And the iron bar goes through it, right? And this cylinder here is copper. And then inside is vinegar, which acts as the electrolyte solution. So I don't know if you can see that super well, but there's a bit of liquid kind of in here, and that's the electrolyte solution. So yeah, of course.
Yeah, so now I'll be talking a bit about primary and secondary batteries. So all the batteries that we use today, they fall into one of 2 domains, primary or secondary batteries. The difference between the two is that for primary batteries, those are your single-use batteries. The batteries in like your toys, your watches, your clocks, those are like your AAA batteries because they're not rechargeable, and they're best for single-use low drain applications. The secondary batteries are like the batteries you would see in your phone or your electric vehicle if you have one, and those are the ones that you are able to recharge daily, and those are best used for like devices that need frequent recharging or long-term energy storage solutions. So here are a few of the main primary batteries. There's I believe there's like over like 50 different types of primary batteries, but these are the most common ones we see today. And I'll talk a bit about them, but you don't need to know very in depth about the chemistry of each one. They're pretty similar though. So zinc carbon alkaline batteries, those are the batteries you would see in your toys, your alarm clocks, your flashlights, your remote controls. As you can see on the volts, they're both 1.5 volts per cell, which is actually like pretty low for a battery. So those are your like single-use batteries that are used for lower drain applications. So the advantages of each of them for zinc carbons that it's it doesn't cost a lot to make. It is very widely made. It can be distributed very easily, and it's widely available. It's accessible. Like if you go to your CVS or your local Walmart, you'll see like AAA batteries are very easy to find. And for alkaline batteries, they are a bit less. less widely available, but they also have a higher energy density per cell, and they have a longer shelf life, and they have better performance at low temperatures. Like, for example, you might notice that your phone battery, it drains really, really fast when it's cold outside. Or I know Eva has a Tesla. Do you have to recharge it more often when it's cold outside?
I don't have to recharge it more often, but there is actually a specific setting on my electric vehicle for cold weather that helps save energy because the battery drains a lot faster when it's cold outside. So yeah.
Yeah, and the most expensive or high performance of these three is a lithium battery. As you can see, it has double the amount of voltage per cell, which means it has a higher energy density, and it has a long shelf life also, which is very important. It means you can store it for a long time before you actually have to use it. And it is extremely lightweight, and it has reliable performance across a wide range of temperatures. So these would be used in higher drain applications like watches, calculators, medical devices, remote sensors, and military equipment, like stuff that you don't want to be able to have them not be charged at one time. Do you want to go to the next slide? So these are some types of secondary batteries. Like we talked about before, these are batteries that you can recharge and reuse over and over again. And so nickel, cadmium, these are the robust batteries that can tolerate a lot of different temperatures, and it has a high discharge rate. And these are typically 1.2 volts per cell, and these are used in for example, like power tools, emergency lighting, and industrial applications. And typically for secondary batteries, lithium batteries are considered like the best ones, even though they're a lot more expensive. They just work a lot better because they have, as you can see, they have more voltage per cell, and they have a higher energy density. They're extremely lightweight, which is really good if you want to put it in, for example, in your phone or your computer, something that you don't want it to weigh a lot because of the battery. And they also have a long cycle life. So typically these are used, for example, for lithium ion. They're used in smartphones, laptops, electric vehicles, and energy storage systems. And lithium iron ones, they're used in power tools, electric vehicles, and solar energy storage. Next slide. So now I'm going to compare and contrast like the different batteries in cars. You might notice that there's been a lot of electric vehicles on the rise lately, like Teslas, for example. I've been seeing more and more Teslas on the roads recently, and that is because of how you don't have to go get gas. For electric vehicles, they're powered entirely by the battery inside the vehicle, while for traditional car batteries, well, traditional cars also do have batteries. They're not powered by the battery inside. They're instead fully they're powered by like the gas that you put into the tank. So the batteries between these two cars are a bit different because of that. So for traditional cars batteries, the primary function of this battery is to provide power for starting the engine and running accessories rather than powering and propelling the entire vehicle. So typically the voltage is lower at 12 volts per cell, and the energy density is rather low, and the cycle life, which is the number of times you can use this battery before it's like considered not great for use anymore. It's 300 to 500 cycles, and the charging time, it's not applicable because you can't charge a traditional car. It's typically pretty lightweight because it doesn't have to hold that much energy. There's not much to the battery because it doesn't do as much as electric vehicle battery does. And the environmental impact is that it contains the toxic lead, but it's pretty recyclable because we've had traditional cars for a long, long time now. So there has been a lot more infrastructure to support how to properly dispose of these batteries. And the cost of them is pretty low because they're not powering the entire vehicle. So for electric car batteries, they're like we talked about before, they're the lithium-ion batteries. Lithium's very, very good for secondary batteries. So the primary function of it is it powers the entire vehicle, including the motor and electronics. So therefore, it needs to have a very high voltage. So typically, it ranges from 200 volts to 800 volts, depending on the vehicle model. And it has a high energy density, and it has a high cycle life because, as you can see, it's like normally over 1,000, because you want to be able to use this battery over and over again before you actually have to change it out. And the charging time, it varies. It depends on whether it has like you're charging at home or you're charging at like another Tesla station. I believe those exist, right? And these are pretty heavy batteries. They need to be heavy because they need to contain a lot of energy and a lot of voltage. So that means they're a lot more heavy than traditional car batteries. And the what it contains, actually, it has a pretty heavy environmental impact because it requires rare earth materials, and the infrastructure for recycling these is quickly emerging as the demand for these vehicles increase over time. So some similarities / an overview of them. Both of these store chemical energy and convert it to electric energy to power the vehicle. And both types are recyclable, even though the processes differ due to their chemical compositions. And both are essential for vehicle operation, even though they power different functions. And traditional batteries primarily support engine and ignition and low power accessories, and they have a simple and robust design. And for electric vehicles, they're the central power source for propulsion, which meaning it requires a higher energy capacity, advanced chemistry, and it's typically larger. So now I'm going to talk a bit about the sustainability behind batteries. Like what you might notice that there's 4 different stages of it, essentially. There's the raw material extraction, like what materials we actually need to make these batteries and how does it impact the environment. The manufacturing process, how these batteries are made, the life cycle / longevity of the batteries, and how they're normally disposed and recycled. So first, I want to ask everybody, how do you normally dispose of your own batteries? Do you just throw them in the trash? Do you go to a special place for them? Yeah.
I've been keeping mine in my drawer waiting for you guys to come and hoping that you'd be able to help me with what to do with them.
Or I've taken them to our transfer station, asking them where to deposit them. No, go ahead.
Yeah.
Just go ahead.
We do have a battery transfer person in the audience virtually right now, just so you know. Thank you for what you do. But he works at the transfer station in town.
Wow, perfect. Maybe you can share some insights with us later about how to properly dispose of these. So before doing this talk, I actually had no clue how to dispose of batteries properly. I just handed them to my mom or my dad and had them dispose of them. What about you, Eva?
I have to say the same. I haven't really been in charge of disposing batteries before, but I know that a lot of batteries are sold and they come with a lot of warnings and you can't quite just throw them in the trash.
Right. So first, anyone else? All right, I'll get straight into it. I'm going to go straight into first raw material extraction. So for batteries, they contain a lot of rare earth metals like lithium, cobalt, and nickel, which can lead to, when we extract them, it can lead to habitat destruction and it can pollute the surrounding environment. So especially for lead extraction, it poses significant health and environmental risks for all involved and those surrounding the area. So some solutions, or like not solutions rather, but like helpful things that we have done recently or over time to combat this destruction is ethical sourcing of materials. That means becoming less reliant on mining for these, but rather like recycling materials and developing alternative chemistries. Like for example, sodium-ion batteries are becoming more and more popular because the materials used to make them are very abundant in the world and they don't take that much energy and are not harmful to the environment when we have to mine for them. The second part of this cycle is the manufacturing process. So making batteries is a very extensive process that obviously has to cause, that obviously like pollutes the world because of how much energy it consumes to produce these batteries. And they're often powered by fossil fuels, so emissions of greenhouse gases are very common with these, with this part of the cycle. And so some sustainable practices that we're establishing, that that more people are utilizing is using renewable energy in manufacturing and improving the efficiency and reducing the waste during the production process. And the third part of this cycle is the lifetime and longevity of a battery. So as you may know, like all these disposable batteries, you have to change them out every once in a while because they run out of charge. And if a battery has a shorter lifespan, that means we have to use more and more batteries, and that creates more and more toxic waste. So basically, some sustainable practices that more people have been utilizing is extending the battery life through better design and technology, like more volts per cell, and extending the amount of cycles. And this can mean improving the energy density and reducing degradation rates. The last part that I wanted to talk about is recycling and disposing of these batteries. So many batteries are not recycled properly due to technical and economic barriers and a lack of proper education surrounding it. Because batteries, as abundant as they are in our society, we don't normally think of them as something very important or something that we rely on every day. Yeah, we typically just toss them in the trash. So this can release toxic materials into the surrounding soil, water sources, and even air if they're not disposed of properly. And there has been more and more advanced recycling technologies to try to recover the rare earth metals that we talked about in step 1 so that we don't have to mine for them again. And there has been more policies for battery collection and proper disposal. Like, for example, you said someone in the audience was actually in charge of that. Yeah, that's great to hear. Next slide. I believe we have some questions coming up. Do you think companies should be held responsible for the entire life cycle of batteries, including recycling, or should it be a shared responsibility with consumers?
Yeah, so a couple of interesting considerations when you think about some answers to this question is that a lot of companies right now don't have motives to treat their battery use and battery disposal ethically. It's a lot of work for them that doesn't come with a lot of benefit, and certainly not financial benefit, right? So is it something that the companies themselves should be entirely responsible for because they're the ones that are putting these batteries in the products in the first place? They're the ones that probably know the details of the batteries and why they're using them, where they're sourcing them from, and they should be in charge of making sure that their consumers are informed on how to handle their products because at the end of the day, they're the company producing them? Or is this something that should really be a public burden? Is this something that we should try to get the general public to really understand and really know and research, and then they should be treating all the products that they buy very carefully and looking at those batteries very carefully and making sure they dispose of them very properly? Like, where do you think that responsibility necessarily falls, and where do you think it would be most effective? You're saying that you think the responsibility should be shared between the company and the consumers, right? And that it should be a little bit of each.
Yeah, I wanted to give you something else to consider. If companies should be responsible for also disposing of these batteries, what if the prices for these batteries were to raise? Would that change your answer of whether we ourselves should be responsible for disposing of them, or should companies dispose of them? Another question for you guys. Should governments impose stricter regulations on battery manufacturing and disposal, even if it raises consumer costs? This was kind of connected to the question I just asked, but should do you believe these restrictions should be like community-based or town-based or government-based? Like, at what level do you think the responsibility for educating the public should fall?
All three.
All three?
Yeah, Sydney, you make a great point that there's a difference between having the responsibility be community-based versus having the responsibility be company-based versus having the responsibility be government-based. And I like to think of it that there are some pros and cons to each. And you just mentioned a great pro, is that the government is such a large and overarching entity that when they put laws in place, those tend to make a lot of change. Those are regulations that everybody has to follow, right? They're kind of above the companies in that sense. If they put a law in place saying, hey, companies, you need to do this, those companies need to do that, right? And then one of the downsides is that we have to think about the efficacy that happens on each level. So this is something that if we're thinking about the community level, you know, it's a very huge lift to make sure that everybody is properly educated about batteries and about how to dispose of them, and there are all these different types of batteries, right? So that's something that is very difficult to achieve, and then it's less strict and it's less sure because there's kind of always going to be that one person that doesn't do it, and there's kind of always going to be negligence or people who are uneducated, right? So that's a downside of pushing for the responsibility to be on the community, right? And then as far as holding manufacturers accountable or having it at the government level, the US government can only really impose such strict regulations on companies in the United States, right? So there are a lot of manufacturers that are overseas, and the US government doesn't have the same hand in affecting those companies or regulating those companies that they do the companies in the US, right? So there's a downside there as well. Yeah, so Bob's question here is that when you go to Costco, for example, and you buy a pack of your regular Duracell batteries, there aren't instructions on how to dispose of them, is what you're saying?
Yeah.
I think it's real small.
I think there's a regulation that batteries do come with some instructions, but there are a lot of people that don't know this, right? It's kind of the tiny packaging or the tiny words that are on the side of the packaging, or the little packet that falls out and you don't really see it and you don't really think about it and nobody reads it because no one can even see that. It's like so tiny. So that's an example of some efforts to educate the public that haven't been as effective because a lot of people just don't see those packets or don't know about that information. But
Right. So now I'm going to talk about some new and upcoming alternatives and solutions that have been made to try to help this practice of batteries become more sustainable. So the first one we talked about briefly before, sodium-ion batteries. The materials to make these batteries are very abundant and environmentally friendly, so they're a great option. And the second one is green hydrogen. This means energy storage using clean fuels. The third one is second life applications, like, for example, repurposing old electric vehicle batteries for energy storage systems in homes or on the grid. And the last one is regulations and standards have been, governments have been making more and more regulations and standards encouraging sustainable practices and responsible recycling for both companies and consumers. And now Eva's going to talk about a new and upcoming technology that is very applicable.
yeah, so like Sophia says, we have some strategies, some practices that are in place now that we use as alternatives or solutions to make our batteries more sustainable, more energy efficient. But there's also some really promising technology on the horizon, especially because batteries are such a ubiquitous, popular technology that's kind of just used in everything. This is a very powerful area of technology, right? And one of the most promising upcoming technologies is what are called solid-state batteries. So to give you an understanding of what solid-state batteries are exactly, I'm going to compare them to lithium-ion batteries. And these are the batteries that Sophia introduced earlier. They're kind of our best batteries. They're used in those electric vehicles. This is what is in your phone right now. Those are lithium-ion batteries. So what's the difference between these new solid-state batteries and the batteries that we're using right now? Well, as it turns out, the cathodes are very similar. They're made of the same materials. And the anodes are slightly different. The current batteries we use now use graphite. And in solid-state batteries, they would most likely use lithium metal. But the biggest difference happens in the electrolyte. So the electrolytes in the batteries that we use currently are liquid. They're a liquid substance. And in solid-state batteries, and this is why they're called solid-state batteries, that electrolyte is actually made of a solid. So if you move to the next slide. So what are the implications of this? What are the impacts of this? Why is this such an improvement? Well, there are a lot of different areas that this impacts. And firstly is safety. So you guys might know, or you might have heard of a bunch of issues with batteries, right? Battery leak issues. A couple of years ago, Samsung released a line of phones, and then when you charged them for too long, they started blowing up, and that was a problem because the battery would overheat and explode. So if you really think about batteries, we have a bunch of really reactive chemicals put together in a system that starts heating up when you use it, right? Because batteries, as the electrons flow and they face resistance, that resistance generates excess heat energy. And that's why batteries heat up, right, as they typically do. You might have noticed that on your phone or your computer if you run it for too long or something. So batteries actually have posed like quite a bit of a safety risk. And the electrolyte in particular is susceptible to leakage. And once that electrolyte leaks out, it can damage your electronics. It can get in the mouths or on the skin of children, which you really don't want it to, right? Because again, these are hazardous chemicals. And literally just by virtue of being a solid, right, in these solid state batteries, it reduces the risk of leakage, it reduces the risk of batteries exploding or getting set on fire, which we've seen a lot of in the past, as I've said. So that makes these batteries a lot safer, and that's a great thing. The next thing is that they're a lot more energy dense. So this just means that you can make a battery, right, that is the same size as a lithium-ion battery, and this solid-state battery will hold a lot more energy in it. And this is great for manufacturing purposes. We're always trying to make things smaller and more efficient, and that's why energy density has such huge implications, right? And then durability. So also by virtue of being a solid material, this new electrolyte allows the battery to get hotter, to get to a new temperature, a higher temperature than lithium-ion batteries can reach, while still being safe, right? So it's less prone to bursting into flames, essentially, and it can withstand higher temperatures without being dangerous. So that means you can run more current through it, and you can make these batteries that discharge higher amounts of current at a time. And then there's also longevity. So instead of a high intensity, these batteries kind of last a longer time. Like we said before, you use them up, and then you charge them again, and then you use them up, and then you charge them again. And those are called life cycles. And these solid-state batteries would have more life cycles before they deteriorated and lost energy than lithium-ion batteries that we use now. So if one thing that I like to point out is that everybody's phone, which probably has a lithium-ion battery in it now, has what's called battery health. And you guys can check this all on your phones right now. You can go into your settings app and look up your battery health, and it will give you a percentage. So for example, my battery percentage is 74%, and that means that when I charge my phone up all the way and it says 100%, that's only actually 74% of the energy that it originally had when I bought it brand new. And that's because the battery deteriorates over time, right? So if you're annoyed that your battery runs out, your phone dies too fast, right? These solid-state batteries are much better. They'll last longer, and they'll give you a longer life cycle, so maybe my phone wouldn't be on 74% battery health.
Do they sell these batteries today?
No, these are a future technology, so they're kind of in the works, yeah, of being processed and being moved into manufacturing. But I think that they are kind of looking at using them in watches right now. So it's in the process of being moved into all our devices and worked into the market and everything, but I know some small watches might have them. So, yeah. And then there's another thing, all these implications or all these improvements, right, that solid-state batteries have, higher safety, higher energy density, more durability. They have a lot of potential to provide us with environmental benefits. One of the biggest ways they can do this is through electric vehicles. So we all kind of understand that electric vehicles are a lot better for the planet than our gas cars. But one of the biggest issues with electric vehicles is that they're so heavy. Batteries are really, really heavy, and they weigh the car down. And it causes the car, ironically, to need more battery to push it forward, right? Because all of a sudden this car has gotten so heavy. So CO2 road travel right now accounts for approximately 15% of all global CO2 emissions. So if we had all electric vehicles, that would reduce the amount of global CO2 emissions by quite a bit, of course, because we rely so much on fossil fuels for travel. Quite a bit. Yes. And solid-state batteries have, as you can imagine, a lot of potential for use in electric vehicles. By being more energy dense, we can get the amount of energy we need to run this car without it weighing so much, right? And it actually takes less materials as well. As you can imagine, you build a smaller battery, you don't need to mine quite as many materials. And this could actually reduce the climate impact of batteries by 39% compared to lithium-ion batteries, just because it uses less material, right? And then the last thing I want to talk about has to do with the electricity grid. So right now, we have a lot of technologies at our disposal to produce renewable energy, right? Clean energy. But one of the biggest problems with renewable energies is that they're not so convenient. When we have fossil fuels, we can just carry them around with us, and whenever we need that energy, we just burn it and we have it, right? And that's what you do in all gas cars, right? You carry around gasoline, when you need it, you burn it, and you run the engine. But with renewable energies, solar panels, for example, you only generate solar energy when the sun shines. You can only get wind energy when the wind blows. And this limits us in a lot of ways. And it also creates a bit of a problem because it stresses the electricity grid, right? The electricity grid doesn't do well under fluctuation. So that means that, for example, one of the biggest issues that's happening right now is what's called the duck curve. So if you go to a place like California, for example, there are a lot of people who have solar panels on the roof of their houses. And that means that the demand on the electricity grid looks something like this throughout the day. At the start of the day, everybody's waking up and they start using a bunch of electricity in their houses. And the demand goes way up. The sun hasn't quite risen yet, and there isn't a lot of solar energy being generated. But in the middle of the day, all of a sudden, a ton of solar energy is being generated, and everybody starts using that. So all this demand drives way down, and all of a sudden, we kind of need to stop all the energy running, all the electricity running through the grid, right? But then later at night, when the sun starts coming down and people are still, they're getting ready for bed, they're eating dinner, they're still using their appliances in their household, the demand goes way up again. And that fluctuation, that back and forth, is really, really bad for the electricity grid. The solution to this is storage. If we can generate solar energy, wind energy, and then we can put it in a battery, and then we can just discharge that battery when we need that energy, then we don't need to have those huge fluctuations in the electricity grid, and we can take some of that pressure off our grid, and we can rely more on renewable energies. So having new batteries that can store record amounts of energy in less material is really, really helpful. That's something that we want and we need for the future to strengthen our electricity grid. So these solid-state batteries have huge potential to be used in large-scale electricity grid storage. Right. And, well, so we've been talking about the environmental benefits of these batteries, right? And while there's a lot, and while they sound quite great with all these benefits that I've been talking about, there are a few downsides as well. So when I was talking about the materials that are used in solid-state batteries versus lithium-ion batteries earlier, you might have noticed that there is a lot of lithium in these solid-state batteries, and they have a higher density of lithium in them. This means that if we are to transition, hypothetically in the future, if we are to transition to start using solid-state batteries, what's going to accompany that is a rise in demand for lithium and therefore lithium mining. And this is something that Sophia was talking about a little bit earlier, right? This is the rare earth metals, right? And the mining is harmful, of course. It's not as harmful as fossil fuel mining, but it still has negative impacts. And a good thing to note is that these impacts, a lot of them are concentrated in the surrounding area right around that lithium mine. It pollutes local water sources, it hurts the habitats nearby, and this stress means that the countries that do lithium mining, right, that have lithium mining, are hurt most by the lithium mining, right? Those impacts are concentrated in those areas and in their countries. So one thing that we want to consider is that the countries which control the production and the manufacturing of batteries and sell that high-level product and gain the most margins and the most profits from it aren't actually necessarily the countries that are doing the most lithium mining, right? So the top 3 lithium-producing countries in the world are China, Chile, and Australia. And while China is actually the #1 producer of batteries worldwide, Europe and the United States account for most of the remaining production, right? So this means that countries like Australia and Chile, they're suffering the negative impacts of having these lithium mines in their country and destroying their habitats, while the majority of the profits are actually going to countries that manufacture the batteries. And so there's a bit of a gap and an injustice in that sense, right? So I wanted to ask you all a question. Do you think that the environmental benefits of electric vehicles are outweighed by the negative impacts of mining materials for batteries?
Right. Like we talked about before, with traditional cars, with the gas you put into your tank, the exhaust fumes, like they do a lot of damage to our planet because the gases that it produces are not very good. But with traditional vehicles, with electric vehicles, we don't have this concern because they don't produce these, they don't use these fuels. But they use a lot of lithium. So the mining for this lithium is extremely harmful to our planet. So do we consider this is a one-time thing, though? Like once you have the materials to make the batteries for this car, you don't need to mine for it again and again. But with traditional cars, you will be releasing like gases into the planet over and over again as you drive the vehicle. So is the one-time impact of mining for this lithium outweighed by like its benefits because we don't have to put gas into the tank and have it release fuels into the planet? Or
Thanks. Well, there's not much global warming from lithium, so to my mind, that's priority. The 5 major mass extinctions, all due to CO2 pumped into the air by volcanism. And so I'd much rather go for clean air and deal with the lithium. And I suppose those countries where they produce lots of lithium see very little bipolar behavior, as that's the medicine to put it to rest. But I'm a nuclear energy person, molten salt reactors.
that's a great point. With electric vehicles don't have CO2 productions, which cause a lot of global warming. But with lithium production, like you mentioned before, America is not a country that produces a lot of lithium. It's not a country that mines for a lot. So the countries that the mining takes place will definitely experience a lot more different impacts and might have different opinions.
Yeah, and you do make a good point, and it's like I say earlier that the lithium mining isn't nearly as harmful as drilling for fossil fuels, right? So if we just look at those impacts side by side, maybe you say, okay, well, lesser of 2 evils, right? Let's go for the lithium mining. But there are a couple of things that you might not know about electric vehicles that are interesting to consider. So I have an electric vehicle, and when I take my car to a charging station, for example, and I plug it in, well, they have electricity flowing into my car, but I don't know how that electricity is generated. And oftentimes, that electricity is actually generated by burning fossil fuels, right? So it's a little bit of a circular, logic there, which is kind of unfortunate. And that's also why relying more on renewable energies is a great next step or forward step, right? Yeah, so just so that everybody can hear it, you made an amazing point, which is about the efficiency of engines in cars. And this is something that I don't think a lot of people know, but like you said, the efficiency of gas cars is about 25 to 30%, and the efficiency of motors in electric cars are about 90, and some claim to be higher, but that's pretty crazy. But those motors are more efficient, and what that means is that when you take in energy, you're using 90% of that energy, right? So in a gas car, you have a certain amount of energy that comes with all the fossil fuel that you buy, right? All the gasoline that goes into your car. And then when you burn all that stuff and you use it to run your car, only 30% of all that energy is kind of used to make your car go or to do the things that you want it to do. So yeah, that's something that a lot of people might not know about. When you go home, you you can think about that you're paying for 70% of what you're paying for, you're not even really using, because your engine doesn't convert it into energy. Yeah.
Because when you pull in after driving around on a winter day, a cat peeps up on the hood.
Yeah. So that's a good point, that your engine heats up as well, and you're saying your cats like it, which is funny. And yeah, so that's a great point as well in favor of electric vehicles, and there is a lot of evidence to say, I drive one, so I'm a big fan of them, obviously. There is a lot of evidence to say that electric vehicles are a lot more beneficial for the environment than driving a gas car, right? So, yeah.
I think that's the end of everything we've prepared for this discussion. If you have any... Okay. We want to respect everyone's time. It's 3:30, so feel free to leave if you have something else to get to, but we'll be around. We'll stick around if you have any more questions or want to just have any other things to ask.
Yeah. Thank you so much for coming to our talk today. Thank you.